Hello ladies and gentlemen, and welcome to the next part of this episode. This is the last slide from the previous part, just to remind you where we got to. Now I showed you in the previous slide nitrogen 15, since that followed the pattern, and nitrogen 15 is a perfectly stable isotope of nitrogen. It just so happens that around here on Earth it's just not that abundant compared to nitrogen 14, possibly because there's a lot of carbon 14 around that's already decayed to nitrogen 14, for example. Now nitrogen 14 follows the same sort of patterns that we showed you with lithium 6, i.e. has this PM roof attached to the top of it. In fact, what we find with these PM roofs are that they are only stable if they're attached to a single column that contains 3 boxes or less, i.e. nitrogen 14 is the heaviest isotope that this PM roof is stable on. Thus, it is only hydrogen 2, lithium 6, boron 10 and nitrogen 14 that actually contain an odd number of both protons and neutrons, while still producing a stable isotope, as no other appendages contain an odd number of neutrons and protons. Heavier isotopes that contain a PM roof beta positive decay or electron capture, which converts a proton back into a neutron, forming a neutron-neutron roof. The converse is true of these neutron-neutron roofs, in that they are stable on elements heavier than nitrogen 14, but unstable on beta decay beforehand. Later we will be going through all the different types of appendages and nuclear building blocks, and mentioning which ones are stable and which ones are not, and what they decay to. Up to now we have seen that helium-4 boxes can join together to produce columns, and that these columns are the nuclei of the even elements up to calcium. The odd elements are also columns, but these have a NPN hat or a PM roof attached to them. Moreover, some nuclei, for example beryllium-9, actually have 2 appendages attached to them, one at the top and one at the bottom. Lastly, we mentioned that because the PM roof is only stable on columns up to 3 boxes high, and no other appendage contains an odd number of protons and neutrons, then this explains why hydrogen 2, lithium 6, boron 10 and nitrogen 14 are the only stable isotopes containing an odd number of protons and neutrons. The next element after calcium is scandium, and here we show you a diagram of scandium-45, its only stable isotope. Now there are a few things to note here. Firstly, that we've gone from single column elements, that was showed you in the previous video, to this double column structure. Secondly, that these 2 columns are held together with neutrons, and we refer to these as bonding neutrons. In fact, it is this requirement for these bonding neutrons to hold the multiple columns together that explains why the ratio of neutrons to protons required for stability increases with the increasing number of protons. This will become more clear as we go through the video and you see some of the heavier elements. Also, we note that protons could not be used to bond these columns together, as that would result in proton-proton bonding, which is very unstable, and thus the structure would break apart if these were used instead of neutrons. Thirdly, we notice that we have this tall hat structure of a proton-neutron, proton-neutron, proton on the top right hand column. These are more commonly seen in radioactive isotopes, where there is the wrong number of neutrons or protons, and we use wrong here in terms of nature producing an unstable as opposed to a stable structure. In terms of scandium-45, this tall hat is required as a minimum of 4 neutron bonds are required to hold the 2 columns together, as these neutrons must be paired together and be placed both horizontally and vertically. Lastly, regarding this tall hat, it could be argued, well, what about scandium-47, which would have another 2 neutrons? These could be incorporated into the tall hat, connecting the bottom 2 protons together, forming an extra box. Well, that would be a reasonable argument and produce a stable structure. But this is nature we're dealing with, and it doesn't always produce the most obvious structures. Thus, even if a stable version existed, but was outnumbered by an unstable version, then we would consider that isotope unstable. An example of this is potassium-40, which is classified as stable. However, a few of them beta decay to produce calcium-40, and thus we have one dominant version that is stable and a minority that is unstable. In the case of scandium-47, this beta decays to titanium-47, and thus has a different structure entirely than that mentioned. We've sort of argued that there is this break between calcium and scandium, where we go from single column structures that we've previously showed you, which include argon and calcium as two examples, to the newly introduced double column structures. However, it's not so black and white. There is a grey area at the changeover point. Here we show you two examples, being argon 40 and calcium 44, both of which are double column isotopes, with these neutron bonds holding them together. Moreover, the pattern of even elements having full box structures and odd elements having a hat on the top continues with these multi-column elements. Here we start off with chromium 52, which is an even element consisting of only boxes and neutron bonds. Then we go up one element to manganese by just adding a NPN hat to the chromium structure. If we were now to convert the NPN hat to a box by adding a proton, we produce iron 56, and continuing this pattern on, we get the next element, cobalt 59. We should point out here that we have put the hats for both manganese and cobalt in the same location, but any of these structures can be rotated or flipped, it doesn't matter. The important thing is just the pattern, which for cobalt 59 is two columns of 7 and 6 boxes high with 4 neutron bonds plus an NPN hat. So we can continue this pattern on, and here we show you another 3 different elements. The middle 2 diagrams are just showing you 2 different isotopes of zirconium. Again, we can see the building pattern of a hat on an odd element, then just boxes for an even element, and then back to a hat for the next odd element, etc. All of these structures clearly have more neutron bonds than any of the previous elements we've showed you. This is because these elements have taller columns and thus need more strength, i.e. neutron bonds, to hold the 2 columns together. As we can see with zirconium, the exact number of neutron bonds required for stability is another grey area, but the general rule of thumb is that there must be an even number of bonds, all of which are paired together. All that we require from the neutron bonds, other than them being paired, is that some of the pairs are placed horizontally whilst others are vertically, and for them to be spread out over the column, i.e. not all located at one end. These rules mean that the columns are unable to twist or shake sufficiently to break the structure apart. In terms of zirconium 92, the extra 2 neutrons will help with stability compared to zirconium 90. However, the total number of protons remains the same, and are only able to stabilize a certain number of neutrons. Thus, if too many neutron bonds were included into the structure, then it would again become unstable, which occurs for all isotopes of zirconium from 97 upwards. This is the end of the video, but this episode does continue in the next part, so I hope that you will actually join us for that. Lastly, please note that this proposition has not yet been accepted, so don't use it to answer exam questions. However, we would like to hear your views, opinions and questions regarding it, so thank you for watching.